Hello everyone, and welcome to this MathWorks webinar on developing ADAS features using MATLAB, Simulink, and Simulink Real-Time. My name is Abhishek Bhatt. I am an application engineer at the MathWorks working on real-time implementation of algorithms as well as hardware-in-the-loop testing. Before joining MathWorks, I used to work in the automotive industry, and I worked with some really cool people developing full vehicle hardware-in-the-loop test simulators for powertrain and chassis controllers. The main aim was to enable test engineers to do some validation testing inside the labs before going on the test tracks. This webinar is the second webinar of a two-part series. The first webinar, named ADAS Algorithm Design and Prototyping using MATLAB, talks about using real-world sensor data and developing a forward collision warning algorithm. In this webinar, we will augment that forward collision warning algorithm with autonomous emergency braking logic in Simulink and debug hardware issues with Simulink Real-Time. I know a lot of you must have heard about MATLAB and Simulink as well. But did you know that MathWorks along with our hardware partner SpeedGoat have a real-time testing solution, both hardware and software, called Simulink Real-Time? Some people might not know this, and that is what I want to show you today, how all these different MathWorks tools work together seamlessly and help you in testing your ADAS algorithms. I'm sure most of you have heard of Mobileye. They are the market leaders in vision systems for ADAS and autonomous driving. Mobileye is using Simulink Real-Time along with the SpeedGoat hardware to test out their algorithms in real time. Because like Eyal Begon from Mobileye mentioned, it saves them time and is straightforward to use. Scania is another good example. They have developed the sensor fusion and the autonomous emergency braking algorithm and implemented that on production ECUs. Like we can see in this video from Scania, they have this heavy-duty truck stopping on its own based on vision and radar sensor information without any driver intervention. That is amazing. So today, we will show you how Simulink can help you in developing these kinds of algorithms. Since these algorithms need to work in the real world, we will also show you how Simulink Real-Time can help you in debugging hardware problems earlier in the design cycle. In short, we want to show you how Simulink is a common platform for software design and hardware testing. Before we get too deep into the presentation, let me give you a quick preview of where we want to end up today. What I'm trying to do is create a test bench to test my autonomous emergency braking algorithm with real CAN cables and CAN DBC files before going to the actual vehicle. That way, if I see a problem, I can easily rectify it in my office rather than on the test track. In order to do this, we take the forward collision warning and the autonomous emergency braking algorithm and deploy it on one SpeedGoat target computer. Then we take the vehicle and the environment model and deploy that to the other SpeedGoat target computer. Connect these two with a CAN cable, and we have our driving simulator running in real time with CAN interfacing. Let me show you what this hardware setup looks like. So in my office, I have this one SpeedGoat target computer running the control algorithm, and I'm running the vehicle, environment, and the sensor models on this second SpeedGoat target computer. And I'm doing this because my prototype test vehicle isn't ready as yet. This is that CAN cable connecting these two real-time systems. And in order to visualize the signals and get a better understanding of what's happening during the test, we have also augmented Simulink Real-Time with Unreal Gaming Engine, which is running on a separate laptop over here, but will be displayed on this monitor. So if I change the display screen to Unreal Game Visualization, we can see that we are sitting inside our car. Let's call that the Ego vehicle. And there is a red car in front going at a constant speed. Let's call that the target vehicle. In order to manually drive our car around, I have connected an analog joystick to the speed goat machine so that I can accelerate and decelerate my car. With that in mind, let's go for a test drive. If our AEB algorithm is working right, the car should automatically start applying brakes as soon as we get closer to the car in front, without any driver intervention. Let's see if that happens. Let's get up to 30 miles per hour, and I'm letting go of the joystick. As we start getting closer and closer, the car should automatically start applying brakes. Okay, so that worked. Let's look at it in the side view to get an idea of the distances. And this time, let's go a little faster, say 40 miles per hour. So we start accelerating, keep going up, get up to the 40 miles per hour. Okay, now we're getting closer to the car in front and brake, 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 brake. Phew. That was close, but successful. So the system seems to be working. Now tell me, how many of you think that we got this right the very first time we tried it out? Of course, it did not work. In fact, let me show you what happened in one of the intermediate steps during the development. We started moving and got up to speed, and we were expecting the brakes to work since this worked in simulation. We get closer, closer, and crash. Clearly the algorithm did not work as anticipated. So the question was, why did this algorithm fail? In the first webinar, we saw how we resolved some of the issues at a desktop simulation level. Taking that one step further, today we will show you how we designed the autonomous emergency braking algorithm in Simulink and debugged hardware issues on real hardware with Simulink Real-Time. Okay, so let's start with the Simulink models. If we look inside the algorithm, we can see the forward collision warning algorithm here. This was developed in MATLAB, and I'm bringing that into Simulink with the help of a MATLAB function block. The second piece is the autonomous emergency braking logic, also called the AEB logic. Here, we are calculating some thresholding distances based on the ego vehicle speed and the target vehicle velocity and distance. If the distance between the two vehicles reduces below certain threshold values, the AEB state logic, which was designed in Stateflow, sends out a signal to alert the driver, or apply partial brakes, or apply full brakes. Since AEB requires dynamic feedback, we also have the vehicle dynamics and the environment models in the Simulink model, which include the ego vehicle dynamics, the target vehicle dynamics, the coordinate transforms for converting data from world reference to the body reference frame, and a statistical noise model for vision and the radar sensor. The data format or the object lists coming out of the vision and the radar sensors are similar to the format which we can expect over the CAN bus from a real vision sensor and a real radar sensor. The test we are running right now is one of the standard AEB test scenarios where the target vehicle is moving at a constant speed and the ego vehicle is approaching it from behind at a faster speed. Let's run the simulation to see how that works. Oh, one more thing. Most of you know that the most common way of visualizing signals in Simulink is to just drag and drop a scope and connect it to the desired signal, right? But that can become a little unmanageable if you have a lot of signals. In our case, though, we are using Simulink Data Inspector, which shows us the desired signals all in one common user interface. And enabling it is straightforward. You go to a signal, you right-click, and say Stream Signal. Once you do that, every time you hit play in Simulink, a new test run shows up with all the signals. Very handy. Okay, so now let's run the simulation. And when I open up the Simulink Data Inspector, I can see my test run here. I will rename this to Simulation and plot out a few signals. So for starters, let me plot the ego velocity and the target velocity. So we can see that the target is moving at a constant speed and the ego vehicle is moving faster, and then after a point of time it seems to slow down. If we plot the distance, we see that the target vehicle starts at about 110 meters ahead of the ego car. At about 90 meters, the vision and the radar sensors start detecting the car in front. So I'm going to plot out the partial and the full braking threshold distances. And in the last subplot, let me plot the AEB warning stage. Okay, so we can see that when the car in front is far away, the AEB is in standby to stage 0. At some distance, the stage 1 warning is sent out to alert the driver. Since we don't take any action, the cars keep getting closer. As soon as the distance gets lesser than the partial braking threshold, the stage 2 gets activated and the vehicle starts applying partial brakes. But that is not enough, and the distance between the two cars keeps getting smaller and smaller. And as soon as the full braking threshold distance is crossed, stage 3 gets activated and full brakes are applied. As soon as that happens, the distance between the two cars seems to stabilize. So that is the AEB algorithm in action. So in summary, we can develop dynamic systems in Simulink, design state logic in Stateflow, and also automate tests and report generation using Simulink Test. I'm not showing you the automated testing right away since the tests take a long time to run. But I will show you a recorded video of the automated testing at the end of the presentation. Now that we have the simulation testing done, let's run the same test on our test bench simulator. So, like I explained at the start of the presentation, I take my algorithm model, generate a real-time application with Simulink Real-Time, and deploy it on one speedgoat target computer. Then deploy the environment models to the other speedgoat target computer. And this is what those models look like. If you notice, I'm using the exact same algorithm that we used in the closed loop simulation. All I've done is added the speedgoat CAN IO blocks for reading and writing to the CAN bus. Similarly, I've used the test cases and the dynamic models from the simulation, added CAN IO blocks to it, and deployed it to the second target computer. Here is another diagram to explain the hardware setup in my office. Initially, both the target computers are connected to my laptop via Ethernet connection. That is how I deploy the real-time applications to the respective computers. But after I have deployed the real-time application, I am interested in visualizing only the signals coming from the environment model because I'm considering the algorithm as a black box system. And finally, the Unreal Engine is running on a separate laptop and communicating with the environment model via Ethernet. So that is what the setup looks like. Let's move back to the Unreal visualization and run this test. So I start the algorithm, start the vehicle models. Okay, we are moving and we crashed. We had this working properly in simulation, but when we run it on hardware, things seem to break down. Have you all experienced anomalies or erratic behavior while doing any hardware testing? Hardware by nature is difficult to work with, and there can be many things that might have gone wrong here. Maybe the CAN cable that I'm using is damaged. Maybe the CAN termination resistances are missing. Or maybe the algorithm isn't working as expected. I don't know. At this point of time, I'm not sure what the root cause of our problem is. So let's see how different tools in Simulink and Simulink Real-Time can help us in systematically debugging this issue. The first question that naturally comes up is, which is the faulty signal here? What is going wrong? There are so many signals in the algorithm. Which one should we be looking at? Do you remember that we'd use Simulink Data Inspector to visualize signals in simulation? Well, since Simulink Real-Time is so tightly integrated with all the MathWorks tools, Simulink Data Inspector also works with Simulink Real-Time without having to add any additional blocks or changing any settings. It just works. So, as a user, you can use the same user interface to visualize the signals in simulation as well as in real time. If I go back to the Simulink Data Inspector, we can see that we have a new test run. Let's call that real-time underscore faulty breaks. And in the comparison tab, let's compare the simulation results with the Simulink real-time results. We can do that with a click of a button. Okay, so look at the first signal. That's the velocity. So in the simulation, we can see that we've started slowing down, but that did not seem to happen in the real-time test. Okay. How about acceleration? Yeah, same story. So we can see that for the simulation run, we've got partial brakes, full brakes, but in the real-time test run, you actually see a slight bump in the acceleration. So that's weird. Let's look at a few more signals. Let's look at the distance here. Okay, so again, same story. We can see in simulation, we keep getting closer, 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 and then finally the distance gets stabilized. But for the real time, we keep getting closer and closer, and at about 2 meters is when the crash happens. So again, that's wrong. A/B warning. Okay, this is interesting because this is part of the controls itself. So for simulation, we can see we go from stage 0, 1, 2, 3. Interestingly, we see the same thing even for real-time test. We see that we're going from stage 0, 1, 2, 3. So that is correct. That's what it's supposed to happen. Let's look at the next signal here, the brake signal. Okay, that looks wrong. We're looking at the simulation test and we can see that you get up to 25, so partial brakes and then full brakes. But in the real-time test, this value is always down at 0. So let's investigate this one. So at least we have answered the first question. So the brake signal seems to be faulty. That seems to be what is causing the issues. And there might be more, but let's start off with one. So where is this coming from? Like, where is the signal originating? In order to locate the signal, we can easily do that through Simulink Data Inspector. So go to the signal, right click, and click Highlight and Model. And this will take us directly to the location within the model, so it's very easy to find and locate the signals. Okay, so we're looking at the brake signal here. If we go further to the left, we see that there is a signal arbitration block, which I'm using for manual mode driving, so that's how my joystick signals are coming in. And if we go a little further back, we see that this signal is actually coming from the CAN bus. Okay, the CAN message ACU underscore D1. So the faulty brake signal is originating in the CAN block. At this point, there are two possibilities again. One is that the CAN message isn't coming in at all, or maybe the algorithm isn't sending the correct values. But in the Simulink Data Inspector test signals, we just saw that the value of AAB warning is being correctly set. So at least that tells me that the algorithm is doing the right thing. So let's investigate that second piece. Let's see if the CAN message is coming in or not. And for this, we can use the Simulink Real-Time Explorer to analyze signals and parameters in real time. In my case, I want to visualize the CAN message timestamp, which is the hardware timestamp of the incoming CAN message ACO_D1. If that number is incrementing, that means we are receiving new CAN messages as we go along. Okay, so one thing, in order to visualize these signals, you can either dive into the model hierarchy, so you have access to all the signals in the model. But because I don't want to do that, I've already created a signal grouping of the most important signals I want to look at. I can load this up and then start the environment models, start the algorithm, and start looking at the signals. Okay, so we see that the value, the timestamp value, is incrementing. And the warning stage again is going from 0, 1, 2, 3, but the break value is still down to 0. Okay, so that means we're at least receiving the CAN messages. So that tells me that the CAN cable isn't broken. I don't seem to have any termination issues. My pins aren't broken or any of that. So there's no issue with the wiring here because I am receiving the CAN messages. So that gets us to the next question. If we are receiving the CAN message and the algorithm is setting the correct value, what else could be going wrong here? Well, we might be using the wrong DBC file, or maybe the DBC file has changed during the development cycle. And while the CAN DBC files themselves are the standard database files which store the CAN message and signal definitions, the signal scaling and offset within them can change very often during development cycle. This happens all the time. And in fact, that is exactly what the problem was in our case. The old value of the break signal in the DBC file, when I open this up, so the value used to be -127 to 0, and I need it to be 0 to 127 because the scaling has changed. So that is why, because we're using that old DBC file, the value of break signal just never was going above 0 because that's the upper limit. Once we make that change to the DBC file and rerun the test case, the brakes work properly and it prevents a collision. We don't have a crash. So that's good. So we can use Simulink Data Inspector to figure out which signals might be causing issues and use Simulink Data Inspector to compare simulation and real-time data. And then we can visualize those specific signals and parameters in real time using the Simulink Real-Time Explorer, which then helps in debugging the problem here. This is all good, but you know what? I don't want to debug this kind of issue every time on hardware. I would like to prevent this issue in the first place. Again, this is where the tight integration of Simulink and Simulink Real-Time becomes valuable. You can reuse the exact same CAN pack and unpack blocks that we used in Simulink Real-Time in the Simulink model as well. So that way you can capture the signal quantization errors caused by the DBC files, as well as the incorrect scaling issues from within your simulation. And you can do this in a seamless fashion because Simulink and Simulink Real-Time are so tightly integrated together. Now, let's move on to the next piece of tuning and calibration in real time. Let's say you wanted to take this autonomous emergency braking controller out on the test track, connect to a real car, and test it out. As a test engineer, I would like to see some of the parameters and change the calibrations at runtime without having to do any of the rebuild and the recompile of the algorithms. And you can do that by creating instrument panels in Simulink Real-Time Explorer. If you remember from the start of the presentation, this is exactly the use case that Mobileye is using Simulink Real-Time for: prototyping algorithms and calibrating them at runtime. So let me bring up one of the instrument panels that I've already created. Let me load that up. So you can see I have the instrument panel with dials, gauges, push buttons, and some numerical entry fields for changing my calibrations. Let me start the algorithm, start the vehicle model, and after I do this, when I accelerate and decelerate the vehicle using my joystick, I can see those signal values show up on the instrument panel. I can also go ahead and change some of the calibration settings depending upon what is happening on the test track. And while I'm doing that, I can also visualize these signals back in Simulink Data Inspector in streaming mode. So again, you don't have to add new blocks or configure anything separately. If the signal logging works in simulation, that automatically works in real time as well. So let me bring up the Simulink Data Inspector and plot a few of these signals. Let's plot the ego velocity and target distance. I guess I can also plot the braking threshold distances. Okay, so now I can see the values are being streamed directly from the real-time system while I'm driving around. If I accelerate, the velocity goes up. If I apply brakes, we start slowing down. Okay, so this is quite easy to use, right? But here is where it becomes powerful. Since Simulink Real-Time is part of the MathWorks environment, you can access all of this calibration data and the changes you're making directly from MATLAB. And if I just run a simple script, I can bring back all the new calibration values from the SpeedGoat machine and compare those with the base calibrations. And then, if needed, you could also revision control those using Git or SVN. We are using Git for this particular project. Secondly, imagine you were on the test track and something interesting happened. You want to make sure that you've logged that signal so that you can bring it back into your simulation environment and analyze it. You can do this again from Simulink Data Inspector itself by going to the specific test run, right-click, and export that data. Let's rename this as My Test Data. Okay, and once you've exported this, you can access the signals in MATLAB and use the power of MATLAB for data analysis and post-processing depending upon what those signals are. So you can calibrate your algorithms from Simulink Real-Time Explorer by creating instrument panels, and then use Simulink Real-Time API to access and compare that calibration data directly from MATLAB. Okay, so till now, we've seen the debugging of hardware issues with Simulink Data Inspector, tuning and calibration with Simulink Real-Time Explorer, and finally, let's talk about test automation. While we were in the exploratory stage, I can do a lot of testing manually to see what works and what doesn't, which is good. But eventually, I would like to automate all of that testing and reporting especially if I'm planning to do regression tests when the control algorithm changes. So in this video, I have automated all of my testing, analysis, and reporting for the AEB test cases using Simulink Test. Once I start off the test cases, the test manager opens up where I have created the test suite, and you can see the list of all the test cases on the left hand side. You can also see the total number of tests as well as their pass and fail status. On the bottom right hand side, you can see the same setup that I had shown earlier, with the controller running on one speedgoat target computer, the vehicle and the environment models running on the other. And in the background, you can see the Unreal Engine being visualized based on the data it's getting from the environment models. And on all the speedgoat machines, you can also visualize signals by directly connecting a monitor to that machine itself. So that's how I'm visualizing certain signals from the controller directly onto a monitor. And basically, I'm just running one test case after the other in an automated fashion. In some of the test cases, you will see that these passed, so that's a green check mark. And in the other cases, you can see that there's a red cross mark which shows that the test failed. Here comes my favorite part. After the tests are done, Simulink Test can automatically generate the test report. And if you dig in deeper into specific test cases, you can look at the reason why something failed or log certain signals. Also, because all of this data is available to you in MATLAB, you can also automatically run analysis scripts and customize the report by adding more data and more tables howsoever you want. So it's very flexible in that fashion as well. So in summary, MATLAB enables you to develop ADAS algorithms like the forward collision warning algorithm. Simulink enables you to use those algorithms and augment them with stateflow and test them in closed loop. And Simulink Real-Time enables you to take these algorithms and test them on real hardware while interfacing with external sensors and actuators. Having the ability to design and test your ADAS algorithms in the virtual and the real world from one common platform is a very powerful concept. And MathWorks tools like MATLAB, Simulink, and Simulink Real-Time provide you that platform for accelerating the pace of your ADAS algorithm design. For more information about hardware and software, feel free to check out the Simulink Real-Time product page on the MathWorks website at www.mathworks.com. Thank you, and all the best.